In the name of God, the most gracious, the most merciful. The 6th episode, we explained Siemens' philosophy in dealing with the specific ones. And in today's episode, we want to highlight the philosophy of a company. It deals with the same type of protections using. So stay with us. An inspiring figure for the nation's renaissance that consists of, there are 3 areas or segments. The red area, which is, yellow area, which is, and the blue area, which is, it is a fixed horizontal line. This segment starts from the lowest sensitivity value, ending at a point known as, its value is set by the manufacturer, allowing any chosen value to control relay sensitivity. Section 2 has a slope called the method, starting and ending at specific points. And what is its value? It is the value set by the manufacturer, and any value can be chosen to control the sensitivity of the relay. As for Section 2, it has its own slope known as the method, and it starts from one point and ends at another point. The recommended value is 3. As for it is recommended that its value be 40%, and is characterized by the release characteristic. There are 3. As for it is recommended that its value be 40%, and it is characterized by the Father B release character, that it helps you, it gives you the start and end of each section. So you can benefit from these values in finding the equation, unlike Siemens relays, which give you the intersection of the extension of each curve with the x-axis, and then you have to calculate the start and end of each part yourself. As for after the point, the blue curve starts to increase its slope in the area, and this new slope is known as the method, with its recommended value from the manufacturer being 80%. We also notice in this drawing that it is divided into 2 parts, one upper part in purple and the other lower part in green. The difference between them is that the lower area is under curve rules. If the value is above the curve, it will issue a trip signal. This area is called the operational conditioned operating area. If the value is below the curve, no decision issued. This area is called if the percentage of the increases above the curve, it will trigger a trip. This area is called the operant conditional, the conditional operating area. If the value is no trip signal, if percentage exceeds set level, a trip signal prevents incorrect operation. 15% of iPhone, 25% of base current at 50 or 60 hertz. If it exceeds the 6th level, a decision will be made to prevent errors, and the value should be about 15% and should be about 25%. The upper area is free from relay trip conditions. This is the operational or unconditional area, also known as at 25% of the base current at 50 or 60 hertz, the area operates unconditionally. When values reach this level, it signals an emergency, bypassing conditions and harmonic values. This area is called the operational area, meaning the unconditional operating area, and it is also referred to as the reaching a value to this great extent, meaning declaring a state of emergency upon, removing all obstacles and impediments that may prove or delay the operation of the relay, and therefore it is not subject to the conditions of the curve and does not look at the values of the harmonics that it has reached, nor to any type of L, meaning that it has done a bypass on all of them. In short, if the value reaches a really high level, it just turns off its mind and forgets logic, and it issues a trip signal, and that's it. What's the difference between when the line to be protected is in a fault condition, turning it on can lead to the appearance of transient charging currents. These currents can cause. Therefore, I take a precautionary measure by reducing the sensitivity of the relay by increasing the value to the value of the automatically and temporarily. It is determined by the time of the high until these currents pass, and after this time ends, we return the sensitivity of the relay to what it was, to its normal state, where the value is, it's as if I did for a brief period, and then I did it again. It should be noted here that if the measured value of is less than the value of, the relay will issue a trip decision after a time delay of, if the value of is greater than the value in the settings, then the relay will issue a trip decision instantly. This situation can be simulated using what is called the injection device, where we inject two phases. The first phase has a current value equal to 0, while the second phase has a current value less than. If it is greater than the value in the settings, then trip decision will be issued instantly. This situation can be carefully simulated in a controlled manner using what is specifically called the injection device, where we inject two phases. The first phase has a current value equal to 0, while the second phase has a current value less than the value. And with a time greater than all the time, we will notice that a trip decision is issued after the time delay ends, and then we reset it again. But in the second phase, with a current value greater than the value, we will notice that trip decision was issued instantly. However, if the line is operational and in a live state, and then the current value rises, the relay will decide using the feature, we will cut off the sequence in the discriminator. We will cut off the sequence in the discriminator. Is this fault internal or external? If the fault is internal, so we will deal with it through the, and then it trips instantly. However, if the ground detects that this fault is external, it will send a very quick signal to activate what is called to start the countdown, and then issue the trip signal if the current value or the measured value is less than the value of, if the value of the measured karak is greater than the value of the trip should be instantaneous. And this situation can be simulated using the injection device, where we inject two phases. The first phase has a current value of and a time greater than 1. We set it here because we are talking about a situation where the line, as for the first phase or the first case, we were saying that the line was in a fault condition, so we set it to, in the first phase, which is the phase of, we inject on the three phases for more than 1 second. And in the second phase, we inject, and we will all notice that it will trip instantly, and then we reset it again, but with an external voltage value of, with a current value less than the value of, with an external voltage value of, with a current value less than the value of, and at a price greater than time. And we will notice that the decision of dismissal was issued after the expiration of time. We reset it, with more current. The injection device is used in two scenarios, line start and line self-operation. This fault is, thirdly, at transformer start and appearance of connected to high voltage to reduce spark during tap changes. When activated from high voltage, inrush current flows only there, low voltage stays open. Current depends on selected value of the is rich in harmonics. If the value of the, so at the start of the transformer operation, what is typically referred to as the connection is made on the high voltage side because the current there is lower, which reduces the spark generated when changing the tap. So as soon as the transformer is turned on from the high voltage side, an inrush current will flow only from the high voltage side while the low voltage side is still open. This current depends on the selected value of the, and as we mentioned before, the is rich in harmonics. If the measured value is greater than the calculated value from the, and less than the value of, the measured value is greater than the calculated value from the, and less than the value, then a trip decision will not be issued due to, what is the origin of, that exceeded the specified setting value. And the same applies to, however, a trip decision will be issued if the current does not contain a high percentage of these harmonics, which means it has not exceeded the specified setting value. But if the measured value is higher than the value of, then a trip decision will be issued regardless of the percentage of second harmonics present in it. This makes me avoid any issues and wait, especially at the start of transformer operations. It is recommended that this value be greater than or equal to 100% of the, if there is something within the area that needs to be protected, it is recommended that this value be greater than or equal to, provided that the greater than 50% of, but if this condition is not met, must keep the value. It should be greater than or equal to 100% of the setting. As for this, it is recommended that its value be within just 1 second. However, if the transformer is within the area to be protected, it is recommended that its value be around 60 seconds. And the summary is that I use in 3 cases. The first live is the state of the line starting up. The second case is the state that the line is working and a fault occurred SNT. As for the third case, which is the startup of the transformer, how does the system, by distinguishing between internal faults and external faults at the beginning, it is based on, the first is and the second is second and fifth harmonic current analysis. And the third is, the goal of the third analysis is to distinguish between internal and external faults, and its principle of operation is that it makes a comparison between the angle of the vector sum of all the E and the angle of the vector sum of all the, where we can observe through this, current angle difference indicates fault type. 0 angle means both currents enter, feeding a fault. An angle of 180 shows normal flow or external fault. 0 indicates internal fault. In a case, if a current enters and exits, the angle between both currents will be 180 degrees. If the angle is 0, this indicates both currents are entering. Thus, both currents feed a fault. An angle of 180 degrees shows the current is flowing normally or an external fault. But if the angle is 0, this indicates an internal fault. The system distinguishes normal current and external fault by comparing values. It indicates that the current is flowing normally through, or that there is an external fault. However, if the angle between the two currents equals 0, this indicates that there is an internal fault. The system can distinguish between the normal current and the external fault by measuring the value at each end, and then comparing it to the value. It is usually recommended that this be equal to where it is if the value, the measurement is higher than the value, the I minimum negative sequence setting. And with an angle of 180 degrees, this means that the fault is external, and thus it is the lowest value. Considerations are taken into account to make a decision. And if the value size is less than the value of viscosity of 180 degrees, this means that it is the normal load current, so do not take any action. However, if the measured value is higher than the value, but at an angle of 0, this indicates that there is an internal fault, and thus the relay relies on it to make a decision based on observation. And they are the inspiration for a national revival practically, and due to measurement errors resulting from city saturation or the difference in values for each, we must add a safety factor to these angles that distinguish between internal and external faults. So this distinction is not like choosing between black and white. Rather, there is some flexibility in choosing it by using what is called. And the angle, it is usually recommended to be 60 degrees in most cases. And the angle, it is usually recommended to be 60 degrees in most cases to achieve safety and consistency at the same time, but in long lines, detailed studies must be conducted to choose the appropriate angle for the, and this is due to the difference in at the line ends, we set area limits assuming 60 degrees. If the current exceeds this, limits are from 60 to 60 degrees through 0. Thus, area limits are from 60 to 60 degrees, passing 180 degrees. Note, the measured value must exceed the reference. If one or both sides are less, no comparison should be made. The system assigns a default value from minus 60 degrees to 60 degrees, passing through 0, and thus we conclude that the boundaries of the region of L will be from plus 60 degrees to minus 60 degrees, passing through 180 degrees. Here we must note a very important note, which is that the value of L must be higher or greater than L. On both ends, there are meanings, so if one end or both are less than the value, no comparison or measurement should be made. In this case, the system assigns a default value for an angle of 120 degrees. If you pull the readings from, you find that the angle is, if it was close to or equal to that degree, this is an indicator and evidence no comparisons could be made, and thus the fault here has not been classified as either an internal or external fault. The 120 degrees here does not indicate that the fault is in the area. We also want to point out that this feature could also be used in the differential protection of transformers and that is the discovery of faults that may occur in the transformer. What is commonly referred to as, since it is difficult to detect this type of fault using the traditional method used in differential protection for transformers. The fault occurring between the coil itself falls under the category of unbalanced faults, which means it causes the emergence of an inspiring figure for the nation's Renaissance. Now let's move on to a new question, which is what happens when we activate were we in the fourth episode, there are between phases themselves or between each phase and the ground, and these capacitors can create what is called charging currents, and which can be seen as if it were, and this can cause incorrect operation of and the value of the charging current depends on where the value can be calculated. The bus in the sequence will charge the decurrent. The bus in the sequence will charge the decurrent. Through this equation, we notice that the more the value of the system voltage increases, as the value of increases, the value of it decreases. We use the technique to address this. It collects all at the fundamental frequency, subtracting from the actual. When activated, this technique collects data at the fundamental frequency, subtracting it from the actual to approach zero, preventing errors and ensuring high sensitivity. Eliminated currents are listed under a heading, updated every 50 milliseconds. It approaches zero under normal conditions, which helps me avoid significant errors in actual readings and achieve high sensitivity for the device, especially with long overhead lines and cables. This procedure is done for each phase individually, and all the currents that have been eliminated can be read under the heading, which is one of the readings that can be extracted from and it gets updated every 50 milliseconds, as long as the presence is confirmed. And it confirms if there are no outputs and there are no faults, whether internal or external. Additionally, the case of, and so on, to avoid any errors in reading, at the moment of a fault, we freeze this if we detect that there are fault conditions that have been met. Consequently, the values may not be considered when selecting the value. As for the source it comes from the differential charging currents generated from the small differential currents. People from the asymmetry of current transformers, the change inside the protected area. So the summary here is that in the case of equals, while the value of equals, when it is negative, so if is in a certain state, then equals zero, and it should be larger. But if it is in a state, then it will equal, will be 10, 2, it should be greater than or equal to 2, 1 or 2 of the expected. And in general, it is recommended that the final operational settings be greater than or equal to 20% if there is a protected area, it is advisable to increase to be greater than or equal to 30% of this, greater than or equal to 20% of and if there is, in the protected area, it is recommended to increase the setting to be greater than or equal to 30% of this. We tried to simplify it to cover all cases related to the operation of and we will mention some notes on it. The first note is if I noticed a current difference higher than calculated. This signal is transmitted under certain conditions. First, the fault must be internal, not external. Second, voltage and harmonics must be below limits. Third, if activated, the system subtracts values. If current difference remains high, a response is issued. As an internal fault, we consider the voltage and not an external fault. The level of the housing and the harmonic values must be lower than the set limits for them. The third condition is that if it is activated, then we'll subtract the value from the value of, in this case, if the final resultant current difference remains higher than the note will be issued. The second note is that if the value of is higher than, then it will be issued directly, regardless of the presence of any harmonics and regardless of the dependence on. So the goal of this is to address internal faults. And the recommended setting is 120% of the highest total expected errors on the current that may appear on the flexible part protecting at the moment of the fault, which is called, and if the value, the calculated value, is close to the expected maximum value, the moment of short lines set to max 50x. In long lines, value is lower during faults. Calculate for internal faults if simultaneous check below level. It's better to refrain from using it, and canceling it is done by raising its setting value to the maximum, which should equal 50 times in long lines, the value of is often much lower than the value of during internal faults. And it's easy to calculate the third note is that if the fault is classified as an internal fault and it occurs at the same time, if it is less than the level of, it will operate even if the fault is internal. But if it is greater than the value or the level, so the first differential minimum is high, so there won't be any due to the fourth and final note is that if the fault is classified as an external fault, then the value of will be the one that will be adopted solely for issuing, and this means that any value lower than it will not trigger a trip, no matter what. Now, let's take this practical example. Draw. This will be the one adopted solely for issuing. This means that any value lower than it will not trigger a trip, no matter what. Now, let's take this practical example. Draw related to in France then I write the equations related to the extracted from the first step in the drawing is to go to the manual for this and then extract details from it. Now we want to determine the number of lines for this and then find the equation of the straight line for each line individually. After that, we will find the intersection point between each pair of lines. Since you helped us by providing the start and end of each segment, it has become easy to find the intersection point between the first and second lines, which equals 1.25 point, where the represents on the axis, while the represents on the y-axis. As for the common intersection point between the second line and the third line, it can be easily found from the slope equation of the second line, where it is known that the slope equation or method equals over delta, and delta is, and delta is. Therefore, it equals, what does it equal? And this is the value that I want to find now, minus, which is the value present in the original, divided by minus. The value, 40%, is found by subtracting and dividing values. With one variable, we find its value. The value is common in the second and third line equations, helping us find the third line's equation. Divided by, which is the value minus, which is the value of. And since this is an equation with only one variable, we can find the value of this variable, which equals. And since the value is a common value in the equations of the second and third lines, this means we can use it to find the equation of the third line. Therefore, we conclude that we must find this value first. Now, let's assume we want to find a value in the equation of the third line when the value of x equals 4. Therefore, the equation of x will equal, and it's the value we want to find when 4 minus, and it's a value, the common value we found in the first equation, divided by 4 is the value of x. And so the method is section 3, and its value in the sting is 80%, which is the value I want to find, minus. Since this is an equation with one variable, we can find the value of x. If we don't find the value of x, it becomes difficult to determine the values. So we find the value of x from the second section equation first. Each line has its own equation. Two variables in x's equation. Complicate solving. Solve x from the second. So we find the value of x from the second section equation first, and then we take this value to substitute it in. In summary, we have 3 lines, and each line has its own equation. the equation of the first line for x equals a constant value. This equation is used when the value of y ranges from 0 to, and the value in this equation is always constant. As for the equation of the third line, it equals here, we said that it is, and to distinguish it from the second line equation and from the first line equation, now let's go back. Equals, because it's the equation of the third line multiplied by it, which is the value we want to find at y. The equation of the third line minus, and it's a value found at 60 plus. We mentioned that we can find this equation of the second line. And this equation is used when the value is greater than 3 and the expected value is greater than. We can find more than one point on each curve and then test them by injecting a value equal to 3 amps, like A. Then we make sure that no disconnection signal has been issued, as long as the value, did it not exceed the amps? We want to forget it was calculated previously from the equations of the straight line for the second line, and there is a specific one for, we will put it in the description of this video, where you input the values of x in it, and then we put x on each, and it will give it the expected value of x calculated. Notice with me in this table that if we set the value of x to equal 1, then the expected value of y on this x is, if the value of y is set to 3 and the expected value is, in section 3, the expected differential current is 1.9 amperes. Calculate these values manually before using Excel to ensure accuracy. I once received an Excel sheet with incorrect settings, so don't rely on it. An engineer might ask how to inject an I bias of 3 amperes. All relays calculate I differential current similarly, but differ for I bias current. The RAD 670 manual shows the relay selects the highest phase current as I bias. Red, yellow, and blue phases need differential protection. An engineer might ask how to inject 3 amperes. I bias. Relays calculate I differential similarly, but differ for I bias. The RAD 670 manual states the relay uses the highest phase current as I bias for others. Each phase, red, yellow, relay selects highest phase current as I bias. Each phase needs protection. Red is 3A at 0 degree, yellow 0.5A at 240 degree, 120 degree, blue 0.2A at 120 degree, I bias is 3A. Readings multiplied by city ratio. With 800.1, I bias is 2400 for all phases. Red phase differential current is the difference between local and remote currents. Input 3 values with red phase current. 3A over 0 degree. Yellow phase current 0.5A over 120 degree. Blue phase current 0.2A over 120 degree. I bias is 3A. Values are primary times city ratio. Assume city ratio is 800.1. I bias is 2400. This 2400 applies to all phases. So I bias for red, yellow, and blue phases is 2400. Differential current on red phase is the difference between local and remote red phase currents. If we assume that the city ratio is 800 to 1, then the pulled I bias value will be 2400. This 2400 will be applied to the other phases, meaning that the I bias for the red phase is 2400. The I bias for the yellow phase is 2400. And the I bias for the blue phase is also 2400. As for the differential current on the red phase, it is the difference between local red phase current and the remote red phase current. I differential 3 amperes, 3 times 800, city ratio, Douglas 2400 amperes. And value equals 3 amperes. Relay readings give primary value. 3 times 800 to 1 equals 2400 amperes. I differential line 2, 0.5 times 800 to 1 equals 400 amperes. I differential line 3, 0.2 times 800 to 1 equals 160 amperes. With I bias at 3 amperes, differential current is 1.1 amperes, so it must exceed 1.1 amperes. As for I differential line 2, it will be 0.5 multiplied by 800 to 1, which equals 400 amperes. As for I differential line 3, it will be 0.2 multiplied by 800 to 1, which equals 160 amperes. And as we mentioned before, when the I bias value is 3 amperes, the calculated differential current from the differential characteristic will be 1.1 amperes, which means that the differential value must exceed 1.1 amperes to trigger a trip signal. Relay trips red phase as L1 is 3 over 1.1A, it equals 3. Since the value exceeds 1.1 amperes, the relay trips the red phase. I differential L2 is 0.5 and L3 is 0.2, both below 1.1, so no trip on yellow or blue phases. OR gate generates the differential trip signal, and values below the threshold mean no trip on yellow or blue. The differential may come from any phase, red, yellow, or blue. The output contact closes if a differential trip occurs on any phase, unsuitable to test differential protection. Resulting from: if the differential comes from one of the 3 phases, this means the output contact closes during a differential trip. Testing differential protection with the general output contact is not recommended. The output contact closes during a differential trip on any phase, so testing differential protection with the general output contact is not recommended. It's better to test each phase independently or altogether to see each LED light up for a differential on each phase. Inject current into the local relay. I red phase at 3 amperes, 0 degrees. I yellow at 0.5 amperes, 240 degrees. I blue at 0.2 amperes, 120 degrees. The red phase LED will light up. Increase yellow phase current above 1.1 amperes to light its LED, while the red phase LED remains on. Each LED lights up when a differential occurs on its phase. Injecting current into the local relay's 3 phases. I red phase at 3 amperes, 0 angle. I yellow at 0.5, 240 degrees. I blue at 0.2, 120 degrees. Only the red phase LED lights up. The yellow and blue phase LEDs remain off. Increasing yellow phase current above 1.1 amperes turns its LED on. Increasing blue phase current above 1.1 amperes turns its LED on. While the LED stayed off, when we raise the current on the yellow phase over 1.1 amperes, the LED for the differential yellow phase lights up. Similarly, when we raise the current on the blue phase over 1.1 amperes, the LED for the differential blue phase lights up. Thus, yellow and blue phases are tested. For red phase testing, set red phase current to 0 and raise yellow or blue phase current to 3 amperes to stabilize I bias. Then, raise red phase current over 1.1 amperes. Red phase LED lights up. This test ensures LED activates slightly over 1.1 amperes. This verifies the differential characteristic. Repeat with 2 points on each curve. For the first curve, choose start and end points. To test the differential current, set the red phase current to 0, then increase the yellow or blue phase current to 3 amperes. Gradually increase the red phase current until it exceeds 1.1 amperes, causing the differential LED to turn on. Repeat by selecting 2 points on each curve, start and end. Test differential protection at each point for all 3 phases. This concludes today's lecture. The goal of this test is to ensure that the LED will activate as soon as the current slightly exceeds 1.1 amperes. This is the purpose of the test, to verify the differential characteristic. We repeat this process by selecting 2 points on each curve. For the first curve, we choose 2 points, one at the beginning of the line and one at the end. We test differential protection on each point for the 3 phases, and the same is true for the second stage. We choose 2 points, a point at the beginning of the line and a point at its end. Each point represents I eggs, and for each I eggs, it has a different I differential. The goal of choosing a point at the beginning of the line and a point at its end is that if these 2 points are correct, then everything between them is correct. This is enough for today's lecture. Stay tuned for the next episode where we will explain the philosophy of Alstom, which is now GE, in dealing with the relay characteristics of differential protection. Glory be to you, O Allah, and praise be to you. We bear witness that there is no deity but you. We seek your forgiveness and turn to you. We hope to see you in good health.